The nightmare for Russia's armored forces has arrived. The UK announces it will provide depleted uranium armor-piercing shells to Ukraine. It's fair to say that the UK has taken a significant step, as even the United States has refused to admit to providing depleted uranium armor-piercing shells. However, the UK's Deputy Secretary of State for Defense confirmed in a statement the plan to support Ukraine with Challenger 2 main battle tanks. He also mentioned ammunition supplies, including depleted uranium armor-piercing shells. Upon hearing the news, Russia predictably began to protest. When the West initially provided advanced main battle tanks, Russia strongly opposed it but was unable to stop Western aid efforts. With no other option, Russia took a step back, requesting that the West not provide depleted uranium armor-piercing shells when assisting with tanks, as doing so would be seen as a nuclear threat to Russia. After all, such weapons pose a significant threat to Russia's armored forces. What Russia didn't expect was that the UK would completely disregard its threats and still provide Ukraine with depleted uranium armor-piercing shells. The conflict between the UK and Russia surrounding Ukraine runs deep, particularly before the Russo-Ukrainian conflict when a British Type 45 destroyer sailed to Crimea, only to be forced away by live fire from Russian Aerospace Forces fighter jets. This was a significant loss of face for the UK. As a result, after the outbreak of the Russo-Ukrainian conflict, the UK has been wholeheartedly supporting Ukraine. The UK has provided M270 rocket artillery, AGM-84 Harpoon anti-ship missiles, and more, even considering offering cruise missiles. Before the West aided Ukraine with advanced main battle tanks, Western countries had already gathered and sent a large number of Soviet-era tanks to Ukraine. However, these outdated tanks have been mostly destroyed, as their weak armor-piercing capabilities make it difficult for them to pose a threat to Russian tanks on the battlefield. The depleted uranium armor-piercing shells provided by the UK this time are widely recognized for their high armor-piercing capabilities and significant destructive power. Once the Ukrainian forces are equipped with these weapons, it could significantly reduce the combat effectiveness of Russian tanks. Currently, the Challenger 2 is primarily equipped with two types of depleted uranium armor-piercing shells, the earlier L-26A1 and the newer L-27A1 models. Why did the UK choose to provide depleted uranium armor-piercing shells rather than other weapons? When the Challenger 2 first entered service, it revealed a deficiency in firepower. Main battle tanks from various countries adopted large-caliber smoothbore guns, while the Challenger 2 insisted on using the L-30 rifled gun. Although rifled guns have the advantages of higher accuracy and longer range, when firing fin-stabilized armor-piercing discarding sabot (APDS) rounds, the sliding band greatly affects the projectile's muzzle energy. The L-30 rifled gun has a muzzle velocity of about 1,530 meters per second when firing fin-stabilized APDS rounds. In comparison, the German Leopard 2A4 main battle tank's L-44 smoothbore gun, despite having a barrel nearly 1 meter shorter, has a muzzle velocity of up to 1,650 meters per second. The L-55 smoothbore gun used in the Leopard 2A5 and later models has a muzzle velocity of 1,730 meters per second. Besides the gun itself being somewhat insufficient, the performance of the British tank's ammunition has also lagged behind the times. The previously equipped L-23A1 tungsten core armor-piercing shell was the UK's first 120mm fin-stabilized APDS round. Although it has been in service for decades, its penetration depth is only 400 mm, making it difficult to penetrate the frontal armor of the upgraded Russian T-72B3 main battle tank. The other two armor-piercing shells equipped on the Challenger 2 are both depleted uranium shells. The L-26A1 primarily replaced the tungsten core of the L-23A1 armor-piercing shell with depleted uranium material, increasing its armor-piercing capability by more than 15%. The UK's latest L-27A1 depleted uranium armor-piercing shell has a penetration capability roughly equivalent to the DM-53 tungsten alloy armor-piercing shell used by the Leopard 2 series tanks, making it capable of destroying most of Russia's main battle tanks. Therefore, some analysts believe that the UK is concerned that the Challenger 2 tanks provided to Ukraine might not be able to penetrate Russian main battle tanks using conventional shells. As a result, the UK decided to supply depleted uranium armor-piercing shells. Additionally, the service life of shells is typically 15 to 20 years. The two depleted uranium shells equipped by the UK are nearing the end of their service life. Considering the complex processing procedures and relatively high costs of depleted uranium materials, the UK can also use this opportunity to dispose of them by sending them to Ukraine along with the Challenger 2 tanks. The West has repeatedly escalated its military aid to Ukraine with a clear goal: to increase Russia's consumption of resources. The UK's move is intended to open a gateway for the West to supply more advanced and powerful weapons to Ukraine. At the same time as the UK announced its plan, the US Department of Defense also announced plans to accelerate the delivery of M1 main battle tanks to Ukraine. Originally, due to technical reasons, the batch of M1 tanks might not have been delivered for several months. However, according to the latest statement from the Pentagon, the U.S. will directly allocate a batch of M1s from the Army's inventory for refurbishment, with delivery to Ukraine expected this fall. The reason why Russia firmly opposes the provision of depleted uranium shells is that their strong armor-piercing capabilities can cause Russian armored forces to lose their advantage. Depleted uranium shells are considered the most powerful among the ammunition systems of active main battle tanks. They possess not only the flight performance of armor-piercing fin-stabilized discarding SABO (APFSDS) projectiles, but also a greater armor-piercing capability than ordinary armor-piercing shells. They are high-tech ammunition that relies on advanced materials. Generally, there are two main types of shells that tanks fire to penetrate enemy armor: kinetic energy projectiles, such as armor-piercing shells, and chemical energy projectiles, such as high-explosive anti-tank, heat, shells. As the name implies, armor-piercing shells penetrate enemy armor using tremendous kinetic energy. Since armor-piercing shells are kinetic energy projectiles, their effectiveness is related to their flight speed and material density. The higher the speed and density, the better the impact effect. This means that the material density of kinetic energy projectiles must be sufficiently high. Currently, the densest metal is osmium, with a density of 22.59 grams per cubic centimeter, but this material is very brittle and essentially turns to powder upon impact, lacking sufficient toughness. The most common material after that is tungsten, with a density of 19.25 grams per cubic centimeter. However, due to the toughness of tungsten as a metal material, it cannot be used purely as a warhead and is often combined with other metals to create tungsten alloys. In general, well-designed, high-length-to-diameter ratio armor-piercing projectiles lose about 50 meters per second of flight speed for every 1,000 meters traveled after leaving the gun barrel. As a result, the armor-piercing efficiency of depleted uranium shells at 3,000 meters from the gun barrel is equivalent to that of tungsten alloy shells at the gun muzzle. In a battle between two armies, tanks equipped with depleted uranium armor-piercing shells have an absolute advantage in firepower. In addition to their superior armor-piercing capabilities, depleted uranium shells also have greater lethality than ordinary armor-piercing shells. Ordinary armor-piercing shells rely mainly on the fragments generated during penetration to inflict damage on combat personnel inside the driver's compartment. Depleted uranium, on the other hand, has a relatively low ignition point. During the penetration process, most of the uranium is ground into a powder form. Due to friction, a large amount of heat energy is generated, causing the depleted uranium shells to ignite and burn directly, producing temperatures above 3000 degrees Celsius. These high temperatures can melt the armor-piercing projectile and soften the tank's armor, as well as cause extensive damage when the depleted uranium shell enters the tank's compartment. The explosive force and aftereffects far exceed those of ordinary ammunition, making depleted uranium shells the best weapon against modern composite and reactive armor. In addition, depleted uranium rounds contain radioactive elements, making them a type of dirty bomb. The radiation emitted by depleted uranium rounds themselves is minimal, but after exploding and burning, they transform into radioactive uranium oxide powder and aerosols with astonishing power. The United States was the first country to develop depleted uranium rounds. During the Cold War, the two superpowers, the United States and the Soviet Union, maintained a nuclear balance and both had large stockpiles of depleted uranium. The annual cost of handling these depleted uranium stockpiles was considerable. Later, the United States discovered the excellent armor-piercing properties of depleted uranium and began producing armor-piercing rounds from it. There are two main reasons why the United States uses depleted uranium rounds. First, they perform well and have better armor-piercing capabilities than tungsten alloy armor-piercing rounds. Second, depleted uranium rounds are made from nuclear waste and are relatively cheap, giving them a cost advantage. The U.S. military tested the power of depleted uranium armor-piercing rounds during the Gulf War. Tanks hit by these rounds suffered devastating damage. Using depleted uranium armor-piercing rounds, the United States destroyed thousands of enemy T-72 main battle tanks, while none of their own tanks were destroyed. However, depleted uranium rounds are made primarily from a hard alloy containing high concentrations of U-238. Although they perform exceptionally well and are cost-effective, they possess strong chemical toxicity and some radioactivity. Long-term exposure or large-scale use of depleted uranium rounds can cause serious harm to both the environment and human health. The U.S. military used large quantities of depleted uranium rounds in the Gulf War, causing long-term pollution in the affected areas of Iraq. Apart from depleted uranium armor-piercing rounds, depleted uranium is also widely used in armor protection. The American M1A2 main battle tank has long dominated the world's strongest tank rankings due to its two major advantages. The first is its powerful offensive capabilities, equipped with a 120mm smoothbore gun that uses the new M829 series of depleted uranium armor-piercing rounds, capable of penetrating 1,000mm of homogeneous steel armor. The second is its strong defensive capabilities, with the M1A2 tank employing a unique depleted uranium composite armor plate. Among the factors affecting ceramic armor protection performance, density and fracture strength are two important factors. High density can improve the defense against high-speed projectiles, but it also increases the weight of the armor. Fracture strength primarily affects the performance of ceramic armor. Tests have shown that depleted uranium composite armor offers a striking resistance to fin-stabilized sabot rounds equivalent to more than 700mm thick homogeneous steel armor, and protection against hollow charge armor-piercing rounds equivalent to 1,300mm thick homogeneous steel armor. During the second phase of Operation Desert Saber in the Gulf War, a M1A1 tank from the U.S. Army's 24th Mechanized Infantry Division became stuck in a mud pit and was unable to move. Two M88 armored recovery vehicles were unable to rescue the tank, which ultimately had to be abandoned. However, to prevent the enemy from capturing the tank, it had to be destroyed. The U.S. military deployed another M1A1 tank, which fired multiple rounds but could only penetrate the outer steel plate of the trapped tank's turret. With no other choice, the U.S. military deployed more M88 armored recovery vehicles to rescue the trapped M1A1 tank. After detailed inspection, it was found that the tank, which had been hit by 3 consecutive rounds, was not significantly damaged. After replacing the turret in sight, it returned to the battlefield. Even the M1A1's main gun could not penetrate its own depleted uranium armor, let alone a T-72 tank. There is no doubt that depleted uranium is widely used in modern military applications, which is why Russia has reacted so strongly to the UK's provision of depleted uranium rounds. After all, this poses a significant threat to Russian armored forces. Do you think the United States will also provide assistance after the UK's provision of depleted uranium rounds? How will Russia respond? Feel free to discuss these questions in the comments section, and we'll see you in the next episode.